The types and abundances of organisms will also strongly influence the physical and chemical properties of soil. Plants and animals furnish these organic material to the soil. So the humus is overall made out of these organisms, the decay of these organisms. Some soils and bogs, for example, are made up entirely of the organic material. But desert soils, as another example, may contain almost no organic material at all. However, it is rare that any soil would not have any organic material, so 0% is very unlikely. The primary source of organic material to the soils are plants, although animals and an infinite number of these microorganisms also contribute. Decayed matter gives living plants and animals some of the needed nutrients for survival, as we have covered in the last few slides. So the fertility of the soil is partly related to these organic material. Furthermore, the decay of the plant and animal remains cause the formation of various organic acids, which will hasten the weathering process. Organic material also has a high water holding ability, as I said in the first slide or two of this soil part of the presentation. And so by having this high water holding ability, it will aid with water retention of the soils, which, as we had said, is very important. Microorganisms, which include fungi, bacteria, and also some of the single-celled protozoa, will also play an important role in the decay of this plant and animal remains. And then the humus is the end product, as I had said. Some other microorganisms turn atmospheric nitrogen into soil nitrogen, for example, which also increases the soil fertility. And lastly, some burrowing animals mix the mineral and organic portions of the soil, and they will mix them together, which create passages for easier flow of air and of water in between these solid particles. This process of the making of these passages by the burrowing animals is called bioturbation. All right, so now we move on to time as another control for soil formation. Time is an important component of all geologic processes. And that also includes this one of soil formation. The nature of soils is strongly influenced by the length of time processes that have been operating on that soil. If weathering, for example, has been going on for a shorter time, the character of the soil resembles that of the parent material. If the weathering has been ongoing for longer periods of time, then the character of the soil is less alike than that of the parent material, and there will also be more organics within this longer weathered soil. They will have a bigger role for the most part. Other soil forming controls, especially climate, play a bigger role the longer the soil has lived. So time is kind of like an aiding control. Again, most of these controls act together. It's not one or the other, but rather as a combination. A certain thickness of soil that is going to appear in one place versus another will change in the amount of time that is needed for that soil to form from one location to the other. And this is greatly controlled, again, by all of the other controls that we have said, such as climate, animal action, parent material, and as we'll see, also based on topography. But as a general rule, the thicker the soil profile is, the longer it has been forming. Okay, so as an example, this soil profile right here on the right is thicker than this soil profile on the left. And so we assume that the soil profile on the right is older than the one on the left. Lastly, for controls, we have topography. So the lay of the land can vary greatly over short distances, and this variation in topography will lead to the development of a variety of localized soil types. Many of the differences exist because the length and the steepness of the slopes will significantly affect the amount of erosion and the amount of water content within those soils. On steeper slopes, for example, the soils are often poorly developed, and this is due to the rapid runoff of any water that falls on these slopes. This doesn't allow for percolation of the water through the soil or for any vegetation to use that water because there's none. And so hence there's no longer any organic material that decays. Again, because the water flows down fast, water doesn't stay, there's no vegetation to use that water, there's no decay on that soil. On shallower slopes, however, soils have the ability to grow because the water remains there and is not flowing downhill as fast. This allows for the vegetation to actually grow and for further chemical weathering and for organic matter creation, as well as to give soils greater fertility through all of those things. The directions of the slopes, or the directions that the slopes face, will also have a very big effect on soil formation. So for example, in the mid-latitudes of the northern hemisphere, north-facing slopes are going to be wetter as the sun is not hitting them as much and evaporating the water within. This is the same for the south-facing slopes in the southern hemisphere. In contrast, the south-facing slopes in the southern hemisphere, the south-facing slopes in the northern hemisphere are going to be drier as the sun is constantly hitting them and evaporating a greater portion of water in them. And again, this goes the same for the north-facing slopes in the southern hemisphere. So again, although we dealt with all of these controls separately, parent material, climate, animals, time, and topography, in nature they work together towards soil formation in any one place. So because soil forming processes operate from surface downward, soil composition, texture, structure, and color will gradually evolve differently at varying depths. So these vertical differences, which become more apparent the longer the soil has been forming, will divide the soils into layers. These layers we call horizons. And a section through all of these soil horizons is called the soil profile. Okay, so we'll look at that in the next slide. Okay, the soil profile is made up of the following horizons, going from the surface downward in depth. So the O horizon is the first one. The O horizon, which is made up of identifiable decaying matter on top and also more unidentifiable matter below. O horizon stands for organic. Okay, below the O horizon we have the A horizon. So the A horizon is mostly mineral material, but it still contains about 30% of humus, so still quite a bit. Below the A horizon we have the E horizon. The E horizon stands for zone of alluviation. Alluviation means the washing out of finer sediments. As the water percolates downward, it dissolves the soluble inorganic components, right? And carries them down to deeper zones. It dissolves them based on different chemical reactions. Okay, so it carries them down to deeper zones, and this depletion of the minerals from the upper areas is called leaching. All right. So below the E horizon, we have the B horizon. The B horizon is also termed the subsoil. It is the zone of accumulation from all of the materials that have been leached from the horizons above. So this B horizon is also termed zone of accumulation. So, for example, if this accumulation is extreme, there is an impermeable layer that will form towards the bottom of the B horizon called the hardpan. This hardpan sometimes is referred to as caliche, in certain soil types and as duracrust layer in other soil types. So you might have heard of it before. And it basically lets no water through because it has so many mineral accumulation that it doesn't allow for any water to percolate through. Okay, so the combination of O, A, E, and B horizons is referred to as the solum or the true soils. All right, and all of that is explained here on the image, just so you know. So below the solum, we have the sea horizon, and it is characterized by partially altered parent material. So although it has undergoing changes that will eventually make it soil, thus far the sea horizon is just regolith, as we had talked about regolith before. And then after we have the sea horizon, we have the unweathered parent material, or simply unweathered material for the case of transported soils. So again, why do I say that? Because for residual soils, the material underneath is indeed the parent material, but for transported soils, the parent material comes from elsewhere. So the unweathered parent material, I think, is named poorly. It should be unweathered material. Whether it's a parent material or not depends on the type of soils we have. Okay, so that is our soil profile. In the next slide, we'll talk about it a little more. So not all of the soils will have these 5 horizons that we spoke of. The characteristics and the extent of horizon development will vary in different environments. Thus, different localities exhibit soil profiles that can contrast greatly with one another. Also, sometimes the boundaries between these different horizons are hard, but sometimes they're very gradual. So in this case, they're kind of hard boundaries. In this case, they're more gradual. A well-developed soil profile indicates a mature soil, and by a mature soil, I mean one that has been forming over an extended period of time and with the appropriate environmental conditions. And by contrast, some soils that lack horizons altogether are called immature soils. So these are very common on steep slopes, for example, where there is constant runoff and where erosion continually strips away any soil that is on top. So it prevents the development of the soil. So again, we have in this image on the right, we have a very poor immature soils up here in the steep slopes and much more mature soils here on the bottom where the slopes aren't as steep. A classification of soils is done through identification of many soil characteristics, just like almost any classification scheme based on characteristics to identify them. There is a system in place, at least in the US, for soil classification, which is referred to as the soil taxonomy. And it emphasizes the physical and chemical properties of the soil profile, and it is organized on the basis of observable soil characteristics. Within this taxonomy, there are orders as the first category of classification, and it goes all the way down to series as the last category of classification. So there are 6 different categories: orders, and then 4 others, and then series. So the table above shows you a brief description of the 12 basic soil orders. It's table 6.2 in your book, in case you're curious. I will not go through all of these soil descriptions, nor will I ask them in the exam. But if you are curious, you are certainly welcome to go ahead and pause the video and read it, or go to your book and check them out. I should also mention that once you have done all the soil classification in terms of order and all the other different levels of characterization, the number of resulting series are about 2,000, I think, or more. So a lot of different soil types exist. This figure above shows the complex distribution of worldwide soil taxonomy of those 12 different soil types that I told you about in the last slide. The soil taxonomy has certain areas in which it is more useful, like, for example, in agricultural uses. or yeah, agricultural uses. But other areas such as engineering or civil engineering or construction is not as good for identifying those soil types because they're very specific and there's different things that need to be taken into account, such as the rock type and the different geological formations and features underneath.